Welcome to the Explainer. Today we're going deep, I mean really deep, inside the fundamental building block of all modern technology, the silicon wafer. We're going to see how scientists figured out a way to peek inside the solid object without ever having to break it. So let's start with a kind of a wild idea. We always think of microchips as needing to be absolutely perfect, right? But what if I told you that tiny microscopic defects inside these super pure silicon wafers are actually a critical feature? Sometimes they're the enemy for sure, but other times they're the crucial ally that makes our devices work at all. So before we get to the cool new stuff, we gotta look at how things used to be done. How in the world did engineers find these impossibly small imperfections that are locked deep inside a solid piece of silicon? Well, the traditional method was, let's be honest, pretty brutal. First, you literally had to break the wafer. Just snap it in two. Then you'd pour on some corrosive acid to etch away at the surface, which would hopefully make the defects show up. And finally, you'd shove it under a microscope and just start counting. Tediously. One by one. Yeah, you can probably guess the problems here. This whole process didn't just take hours, sometimes days. It completely destroyed the very thing you were trying to inspect. And on top of that, you were only ever looking at a tiny fraction of the wafer, so the picture you got was never really complete or all that accurate. So this slow, destructive method was obviously not going to cut it in the super fast-paced world of making semiconductors. It really pushed scientists to find a better way, to ask that key question: how can we see what's inside the wafer without smashing our sample to bits? And the answer is just a really elegant trip of physics. To you and me, a silicon wafer looks like a shiny, gray mirror. It's totally opaque. But if you could see an infrared light, that same exact wafer becomes almost completely transparent. It's like suddenly having X-ray vision for silicon. This whole principle is the magic behind a much, much smarter tool, the Optical Precipitate Profiler, or OPP for short. It works by shining that infrared light through the wafer and then watching for how the light scatters when it bumps into one of those tiny defects. It lets you see them without ever touching the wafer itself. Okay, so we've got this new tool, the OPP, and it sounds great on paper. It's non-destructive, it uses fancy light, but how do we know it actually works? How do you test its limits and prove it's really better than the old break it and count it method? Well, to figure that out, researchers came up with this really clever experiment. They basically built a test track, an obstacle course for the OOP. They took these incredibly clean silicon wafers and then carefully, deliberately grew defects of different sizes and different densities inside them. This gave them a perfect, known standard to test the machine against. So, what did they find out? This is where it gets really impressive, and we see just how powerful this new technique is. First off, the lower limit of what it can see. The OPP can spot defects as small as 16 nanometers. Now, to give you some perspective, that's about the size of a single virus. We are talking about seeing things on a near molecular level, inside a solid object. It's just wild. They also found this really cool relationship. The signal that the OPP gets, basically how bright a defect appears, it grows with the cube of the defect's radius. So what that means is, if a defect gets just a little bit bigger, it becomes way easier to see. It shines much, much brighter, which is absolutely critical for telling them apart. But it's not perfect. There are limits. If you pack too many of these defects too close together, the view just gets too crowded. The OPP tops out at a density of about 2 × 10⁻⁻⁻ defects per cubic centimeter. Any more than that, and it's like trying to count individual people in a photo of a massive stadium crowd. All the signals just blur together. So let's zoom out. What's the big picture here? What does having this kind of precise, non-destructive measurement actually mean for the phone in your pocket or the computer on your desk? I mean, when you put the two methods next to each other, it's not even a fair fight. The OPP is fast, where the old way was slow. It keeps the wafer perfectly intact. It can scan the entire wafer, not just a little piece of the edge. And it's way, way more accurate. It's a total game changer for quality control. And hey, don't just take my word for it. The researchers who did the work said it themselves. The OPP makes the job faster, simpler, and more accurate. You can't get much clearer than that. And this brings us back to the most important point of all. The goal here isn't to create a perfectly flawless wafer with zero defects. That's not even the point. The real goal is characterization. It's about deeply understanding the size, the density, and the location of these so-called imperfections so that manufacturers can control them, getting rid of the ones that are adversaries and actually using the ones that can be allies. So, in the end, this whole story isn't really about chasing perfection. It's about mastering imperfection. By learning to see this invisible world inside silicon, we gained an entirely new level of control. And that just leaves you with a final thought, right? What's the next invisible world out there, just waiting for the right tool to let us finally see it?